Good evening, GCC College Algebra. We're going to be finishing up Chapter 12 tonight, looking at something called linear programming. Now, linear programming doesn't have anything to do with computer programming. Really, it has to do with programming, which is creating and designing lines. And these lines will be inequalities. There'll be systems of inequalities that we'll have to graph. And then there will be something called an objective function that we have to evaluate. And we're going to be looking at these types of problems. Really, there's two different levels of these types of problems. In level 1, there's not really any meaning behind it. They're just going to give us some inequalities to graph. They'll give us an objective function. We'll have to solve the systems to find the vertices and then evaluate. And then in the second level, a little bit harder, a little bit more going on, are word problems with meaning behind them. All right, so let's take a look at linear programming. By the way, if you do have squared paper, today would be a good day to bring it out. I'm going to be using, I don't know if you can see, this is kind of a graph paper. You can print it off. You can download it online and print it. But this is definitely a good lesson to use graphing paper. All right, here we go. So in the homework tonight, as I said, you've got the two different types. You've got 5 problems of type 1 and 2 problems of type 2. So what I'd like to do is I'd like to look at some sample problems. You have to do numbers 9, 11, 13, 15, and 17. So we're going to do number 10, which says that we want to maximize the equation z equals x plus 3y given the following constraints: x greater than or equal to 0, y greater than or equal to 0, x plus y is greater than or equal to 3, x is less than or equal to 5, I should put commas here to separating them, and y is less than or equal to 7. So these are my constraints, and I want to maximize this function within these constraints. So the way I'm going to do this is I'm going to graph these constraints here. Now, the first one I'm going to do, I'm not going to use graph paper. We're just going to sketch it out here. X greater than or equal to 0, y greater than or equal to 0. Whenever you see these two constraints, it really means that it's a first quadrant only graph. So I only care about the first quadrant. And it looks like my y goes high as 7, my x goes high as 3. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So this right here is a graph of x greater than or equal to 0, y greater than or equal to 0. X greater than 0 is all of this. Y greater than 0 is all of that. So now the next line, x plus y greater than or equal to 3. So for x plus y greater than or equal to 3, if I do my intercepts trip, when x is 0, y is equal to 3. When y is 0, x is equal to 3. Or equal to means a solid line. Oh, I wish I had a ruler. Where's my ruler? I don't have a ruler. I don't know where my ruler is. Solid line. And greater than means I want to shade above. Now, I'm not going to do all of the crazy shading. I'm just going to put a little shading so I know which side of the line that I want. Here, x's are less than or equal to 5. Well, here's where x is equal to 5. The line x equals 5 is a horizontal line right here, or equal to solid line. And I want less than that. I want this side of the line. Y is less than or equal to 7. Here's where y is equal to 7, right here. Solid line, or equal to, less than 7 is underneath. So now, here's where all of my x's are greater than 0. Y is greater than or equal to 0. So if I look at all the shading that's going on here, I'm going to kind of double shade in my feasible region, the solution here. which is going to be all the stuff inside here. My highlighter is not a very good highlighter. In the future, I think I'm just going to do it with shading in. But I graph the system of constraints, and in the second half of this, we actually have to come up with the system of constraints, and I get that this is my region. All right, so the first part of it, graphing this system. Now, we've already done that. Here comes the second part, this whole maximizing this function here. Now, in order to maximize this function, I need to know the vertices of this region. The vertices, the points that bound this region. Now, this one's fairly simple. I don't have to do anything too fancy here. I think right off the graph I can read the points. Now, it's not always going to be that way. Sometimes we might actually have to solve some systems here. But the coordinates of this point are 5, 0. The coordinates of this point are 3, 0. The coordinates of this point are 0, 3. This point is 0, 7. And this point, the x value is 5, the y value is 7. So these are the coordinates of my feasible region. The next thing I want to do, this whole maximizing this function here. So in order to maximize the function, I've got the function z equals x plus 3y. That's the function I'm trying to optimize, and I'm trying to find the maximum value there. So I'm going to pick each one of these points, and I'm going to plug them in. First, the point 0, 3. If I plug that in, x is 0 plus y is 3. 0 plus 9 is 9. Next, the point 3, 0. 3 plus 3 times 0 is 3. See what I'm doing here? For each of these points, I've got an x value and a y value, an x value and a y value, and I'm plugging into this optimal function here. Next, I'm going to take the point 5, 0. Plugging that in, I get 5 plus 3 times 0 is 5. Next, the point 5, 7. And I get 5 plus 3 times 7 is, let's see, 3 times 7 is 21, plus 5 is 26. And then finally, the point 0, 7. And I get 0 plus 3 times 7 is 21. So I took each of the coordinates of the vertices of my feasible region, and I'm evaluating them in the objective function. This is telling me I want to maximize. So I'm looking for the biggest possible value. Here it is, 26. When x is 5 and y is 7, I get a maximum value of 26. If this had said minimize, I would be looking for the smallest value, and then that would be my answer, the 0.30. So the answer here is the 0.57, because it gives me a maximum possible value of 26. So this one was a good starter one, because finding the points was really easy, and then plugging them in to the function wasn't really bad. So this is a really good concept one. We're going to do one more like this, and then we'll do a word problem where we actually have to create the objective function, and we have to create all of these constraints, and then graph it, find the vertices, and evaluate it. So these get harder and harder as we go along. All right, let's take a look at number 18. 18 says I want to maximize the function z equals 2x plus 4y, subject to the following constraints: x greater than or equal to 0, y greater than or equal to 0. And again, whenever you see that, automatically you know it's going to be the first quadrant only graph. The line 2x plus y greater than or equal to 4, and the line x plus y less than or equal to 9. So we're going to do it the same way. We're going to graph these constraints, find the vertices of the feasible region, and then we're going to evaluate those vertices in the objective function. So first quadrant only graph here. Looks like I'm going as high as 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. X greater than 0 means all going this way. Y is greater than or equal to 0 means all of this. 2x plus y is greater than or equal to 4. So let's use our intercepts here. When x is 0, y is 4. 1, 2, 3, 4. When y is 0, divide both sides by 2. It looks like x is 2. And greater than or equal to. Equal to means solid line. Greater than means shade above. X plus y is less than or equal to 9. When x is 0, y is 9. When y is 0, x is 9. Nice straight line joining them. Where is my ruler? I don't know where my ruler is. I wish I had a ruler. And I want this and this. Y is greater than 0. X is greater than or equal to 0. So here's my feasible region. All this region in here. Now I want to identify the vertices of my feasible region. This one's not so bad either. The coordinates, this coordinate is going to be 0, 4. This coordinate is going to be 2, 0. This coordinate is going to be 9, 0. And this coordinate is going to be 0, 9. Oh, you can't see that very good, can you? 0, 4, 2, 0. The coordinates of my vertices there. I want to evaluate this in my objective function. Notice in this one I've only got 4 vertices. My objective function is z equals 2x plus 4y. So each of these points, the point 0, 4, the point 2, 0, the point 9, 0, and the point 0, 9. Substitute it in. So I'm going to get 2 times x, which is 0, plus 4 times y, which is 4. It's going to give me 16. 2 times 2 plus 4 times 0 is 4. 9 times 2 plus 4 times 0. Notice I'm plugging the x value in for x, the y value in for y. 18. And 0 times, I got these backwards, didn't I? This is 2 times 9 and 4 times 0. This is 2 times 0 plus 4 times 9 is 36. So I want to maximize. So my optimal solution is going to be this one right here. The point 0, 9. Gives me the optimal solution, gives me the maximum value in the feasible region. All right, so now what we're doing just with these simple meaningless graphs, graphing, finding the vertices, and evaluating it, the same thing's going to be for the second level of this problem. The second level of this problem is going to be word problems where we are going to have to create the objective function. We're going to have to create the system of constraints and then graph it and evaluate. All right, so for that I've assigned you 2 of those problems. I want you to do problems number 19 and 27. We're going to do 2 very similar problems. I'm going to do problem number 20 from your textbook, which talks about farm management. Now, if you have your textbook, go ahead and look at it. I'll pull the textbook out here so we can kind of look at it and read together from this problem, and then I'll move the textbook away and copy it all down. It says farm management. A farmer has 70 acres of land available for planting, either soybeans or wheat. The cost of preparing the soil, the work days required, and the expected profit per acre planted for each type of crop are given in the following table. Preparation cost per acre for soybeans is $60, wheat is $30. The work days required per acre is 3 work days for soybeans and 4 for wheat. The profit per acre is $180 per soybeans and $100 per wheat. Now, the farmer cannot spend more than $1,800 in preparation costs, and he cannot use more than 120 work days. So how many acres of each crop should be planted to maximize his profit? What is the maximum profit? What is the maximum profit if the farmer is willing to spend no more than $2,400 on preparation? All right, here we go. So I'm going to copy down the table. That's going to be one of the keys here. So in the table, it's got prep cost, and I've got soybeans and wheat, and then I've got work days and profit. The prep cost is $60 for soybeans, $30 for wheat. The work days is 3 days for soybeans, 4 days for wheat, and the profit per acre is $180 for soybeans and $100 for wheat. Now, we do have some constraints here. But before I write the constraints, he can't spend more than $1,800 in prep, and he cannot use more than 120 work days. So the prep cost must be less than 1,800. The work days must total less than 120. These are some constraints here. The profit is going to become part of the objective function in a moment. So what are the variables here? Well, the question asked, how many of each acres must he plant? So what we're going to do is I'm going to say, let's let x equal the number of acres of soybeans and y equal the number of acres of wheat. I do know that he only has 70 acres. So x plus y has to be less than or equal to 70 acres available. All right, that kind of happened really fast. What happened there? The total number of acres of soy that he plants plus the total number of acres of wheat has to be less than or equal to 70 acres. He's only got 70 acres available. That was part of the problem there. But he's also got the prep cost has to be less than 1,800. So $60 per acre of soybeans plus $30 per acre of wheat has to be less than or equal to $1,800. That's a prep cost function. He's also got a constraint with work days. 3 days per acre of soybeans plus 4 days per acre of wheat has to be less than or equal to 120 days. So this is work days. He's only got 120 work days available. So we've got 3 constraints here. There are 2 more. The next 2 are x has to be greater than or equal to 0, y greater than or equal to 0. Okay, so what do those mean? We've seen those in all of the other problems. What do they mean here? Well, x is the number of acres of soybean. He can't plant a negative number of acres of soybean. He cannot plant negative acres of wheat. So the number of acres of soybean has to be greater than or equal to 0 acres. The total number of acres of wheat that he plants has to be greater than or equal to nothing, no acres. He plants no acres of one and just does all of the other crop. Maybe that'll give him his maximum profit. All right, so here we have it. What we have here is our system of constraints. There it is. We've created it. The system of constraints. Now that we've created it, we have to graph it. Oh, by the way, the profit function. Here's the profit function. The profit function, profit is equal to 180x plus 100y. That's going to be my profit function for later. That's what I'm going to try to maximize the profit a little bit later. All right, so let's graph this system here. Now I know I've got a first quadrant only graph. This is where using graph paper would probably be a really good idea. Let's see, I don't know how well you can see that this is graph paper here, but I'm going to use my graph paper on this. I'm going to put the system over here for a moment so that I can really focus on the graph. And again, I wish I had a ruler. I don't know where my ruler is. I was here a moment ago. First quadrant only graph. The x-axis represents the number of acres of soybean. The y-axis represents the number of acres of wheat. And if I look at my constraints and I have to think, well, let's see, how am I going to label my axis? When I take a look at this, well, let's see, y is going to be 70, x is 70. 1800 divided by 30 is 180 divided by 3, which is 60. And let's see, what's my biggest number here? 60s and 70s. I'm going to go to maybe up to about 100. So let's see, how do I want to scale this? 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So I'm just creating a scale where I know that I can make sure that I get everything in there that I want to get in there. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So now let's start graphing the system in here. The first one is the x plus y less than or equal to 70. So on my first one, x plus y equals 70. It looks like my y-intercept 70, my x-intercept 70. It's going to be solid line shaded below. So from 70 to 70 shaded below. This is where, you know what, I don't have a ruler, but I've got this old piece of hunk of wood sitting here. I'm going to use that. And I want to shade below. So I'm just going to put little tick marks so I know which side of the line I'm shading on here. All right, so that is my number of acres available. So anything in here is a total of 70 acres. Anything over here is more than 70 acres. It's no good. So now my prep costs. All right, so let's see. What's my y-intercept? Plug in 0 for x. Divide both sides by 30. And it looks like my y-intercept is 60. And plug in 0 for y. Divide by 60. My x-intercept is 30. So let's see, my y-intercept is 60, my x-intercept is 30, and that's going to be a solid line. That's my prep line, and I have to stay below that in prep. And then the work days, it looks like my y-intercept is 30. My x-intercept is 40. Solid line. Shade below. All right, so where is the feasible region here? The feasible region is going to be, I'm trying to be very careful to color and stay inside the lines. I want to clearly identify the feasible region here. X's have to be greater than or equal to 0, y is greater than or equal to 0, and I have to be below those two lines. There it is. Find the vertices of the feasible region. Well, this is the feasible region. I'm going to have 1, 2, 3, 4 vertices. This one is 0, 0. We know that means he's not going to plant anything. Well, certainly if he doesn't plant anything, he's going to definitely be well within his constraints, but he's not going to make any profit, is he, at that point? This point's easy to read because it's the y-intercept. The coordinates of this point are 0, 30. This point is the x-intercept. The coordinates here are going to be 30, 0. Now this point right here is a little bit more interesting. This is the intersection of the prep and work days. So I need to solve that system. Now prep was 60x plus 30y, and I'm going to make it an equation equals 1800. Whoops, just 1800 there. And work days was 3x plus 4y equals 120, and I need to solve that little system. All right, here we go. So I'm going to leave that equation alone. And I get 60x plus 30y equals 1800. But this equation I'm going to multiply by negative 20. Can you see why? Negative 20 times 3 gives me negative 60x. Negative 20 times 4 gives me negative 80y. Negative 20 times 120 gives me negative 2400. Add them together, and I get negative 50y equals negative 600. Divide both sides by negative 50, and y equals, let's see, 60 divided by 5, 12. All right, so what does that mean, 12? Acres of wheat. So the y-intercept there, because y is wheat, is going to be 12. So something 12. I don't know the x value. I need to find the x value. So I'm going to plug that back in. I'm going to use this equation. 3x plus 4 times y, which is 12, equals 120. 3x plus 48 is 120. Subtract 48. Oh boy, this pen's dying, isn't it? 3x equals 120 minus 48 is, what, 72. X is 24. All right, so I found all the vertices. I told you, finding the vertices in the word problems is usually a little bit harder, a little bit more going on. Now that we found the vertices, we want to evaluate in the objective function. So remember, the objective function was the one about the profit, this one right here. And the profit function, that's what I want to maximize, is $180 per acre of soybean and $100 per acre of the wheat. I want to evaluate each of the different vertices, the points in there. 0, 0, which we know is not going to make any money at all. And then the one that was on the y-intercept, 0, 30. The one that was on the x-intercept, 30, 0. And the one that we had a little hard time finding, 24, 12. So 180 times nothing plus 100 times nothing is nothing. If he doesn't plant any acres of soy and no acres of wheat, he's not going to make any money. What about if he doesn't plant any acres of soy and he plants all wheat? Well, 30 times 100 is $3,000. He'll make $3,000 profit. What about if he only plants soy and no wheat? Does he make the same $3,000? No. It would be 30 times $180. Let's see, 18 and 18, 20, 36, 46, $5,400. That's a lot better. So far, the best bet is don't plant any soy at all. Plant just 30 acres of wheat. But we still got this one. 180 times 24 acres of soy plus $100 times 12 acres of wheat. And if we do that on the calculator, I think we get $5,520. You know what? I'm looking at that in my notes. Let me just make sure that this is correct. Let's see. Here we go. So on the calculator, 180 times 24 plus 100 times 12. Okay, yeah, 5520. So 5520. So my optimal solution, here it is, this will maximize profit. So he should plant 24 acres of X, which was soybeans, and 12 acres of Y, which was wheat. And if he does, the maximum profit is $5,520. There's my answer. How much of each crop should be planted to maximize profit? 24 acres of soy, 12 acres of wheat. What is the maximum profit? $5,500. What about if the farmer is willing to spend, if he changes it, and he's willing to spend no more than $2,400 on prep? This kind of the last part of this problem here. Well, if the farmer changes the constraints and decides, you know what, I'll pay more for prep. I'll pay $2,400 for prep. That's going to change this equation. Instead of 1,800, it's going to be 2,400. The prep line, which was this, which one was the prep line? X is 30. The prep line right here is going to be moved out some more. It's going to be much more. So he'll be able to make a lot more money. You'd have to redo the whole thing with that function. All right, so let's kind of go through this again, just really briefly here. So we had the farmer identifying the variables. X is the number of soy, Y is the number of wheat. The profit function, there it is. The constraints, writing the system. We had a constraint on the acres available, the prep cost, the work days, and of course the fact that X and Y had to be greater than or equal to 0. We graphed the system of inequalities with the shading, find the vertices of the feasible region. One of them was a little tough. One of them we had to treat like a little system of equations. By the way, that's why this problem is in this section, because of this. We have to solve the little system. What method did I use here? I did elimination. I didn't even talk about the method. I just kind of went straight into it, didn't I? I multiplied the bottom equation by -20 so x's would get eliminated. I suppose I could have solved the top equation for y's. If I'd solved it for x's, I'd have fractions, but I could have solved it for y's and substituted. And really, when it comes to solving the system, you can use any method you want. You really can use any method you want. All right, so what I'd like to do now is I want to talk about the two that I've assigned you to do in the homework, and I want to get started on those two. The hardest thing is deciding what the variables should be. So that's where I kind of want to get you started on these problems. All right, here we go. So we're going to look at, the first one I've asked you to do is number 19. And let's take a look at it, read it together. Maximizing profit. A manufacturer of skis produces two types, the downhill and cross-country. Use the following table to determine how many of each kind of ski should be produced to achieve a maximum profit. What is the maximum profit? And what would the profit be if the time available was 4,800? All right, so what we're going to do here is we're going to let x equal the number of downhill skis. Oh, I've run off the screen. So x is the number of downhill skis. Y is going to equal the number of cross-country. All right, so there's my variables. So now I've got constraint. My profit is going to be P equals, let's see, he makes $70 for every downhill, so 70x plus $50 for every cross-country, 50y. There's your objective function. Now what about your constraints? Well, the number of downhill has to be greater or equal to 0, the number of cross-country greater or equal to 0. What other constraints do I have? I have a manufacturing constraint. 2 hours for downhill, 1 hour for cross country, and I've only got 40 hours available. So my manufacturing constraint is going to be 2 hours for every downhill plus 1 hour for every cross country, and that has to be less than or equal to 40 hours. What's another constraint? Finishing time. After they're manufactured, they have to be finished. 1 hour for each of the skis, and I've got a maximum of 32 hours of finishing time available. So 1 hour for every downhill plus 1 hour for every cross country has to be less than or equal to 32 hours. So ladies and gentlemen, there you have it. There is your system of inequalities. 1, 2, 3, 4 of them. Graph these 4 inequalities. Make a nice graph of it. You're going to have 4 vertices. 3 of them will be easy to see. The other one you're going to have to solve a little system and then evaluate all of the points in the profit function. That last part about where you change manufacturing to 48, I don't care about that. If you can do this, that's all I really care about. Now in problem number 27, let's take a look at 27. Is 27 on the screen? There it is, down here, 27. And it's going to be on the top of the next page. It says, maximizing the profit on ice skates. A factory manufactures 2 kinds of ice skates, racing skates and figure skates. We'll stop right there. We know we're going to let X equal the number of racing skates and Y equal the number of figure skates. The racing skates require 6 work hours in the fabrication department. Figure skates require 4 hours. So for fabrication, 6 hours for racing and 4 hours for figure skates. And then the finishing, now notice I don't know how many hours I've got, less than or equal to something. Racing 1 hour, and turn the page, top of the next page here. Figure skates require 2. All right, so let's see. Fabricating department has at most 120 hours. Oh, that's where the 120 is going to go. The finishing department has no more than 40 hours. Oh, that's where the 40 hours is going to go. The profit on each skate is $10 on racing skates is $10 and figure skates is $12. So there's my profit function. $10 per racing, $12 per figure. So here we have it. Here's your system. Here it is. X is the number of racing skates. Y is the number of figure skates. For fabrication, 6 hours per racing and 4 hours per figure. Has to be less than 120 hours available. For finishing, you've got 1 hour for racing and 2 hours for every figure. It has to be less than or equal to 40. And my profit is $10 per racing and $12 per figure. Now, I'm not going to do any more. I want you to do it for the homework. Those 2 word problems, I want you to finish those up for homework. You're going to have to graph the system, find the vertices, evaluate in the objective function. All right, so I want you to go ahead and do homework 13. Not 13. We're about to start chapter 13, actually. This is 12.8. And assignment 12.8 is on page 952. And I want you to do 9 through 17 odd. And these are just graphing, find vertices, and evaluate in the objective function. These are the type 1 problems. And these, if you make a nice graph, finding the vertices is actually pretty easy. You can read them right off your graph if you make a nice graph. And then I want you to do the 2 word problems, numbers 19 and 27, word problems. So the big difference with these is you have to come up with a system. Actually, pause the video, rewind. I've already given you the system, so you should be able to do them. And I want you to email the completed assignment to me. All right, ladies and gentlemen, there it is. Good luck. Get out there. The first part, these I think you'll go through fairly quickly. And since I set these up for you, we should be able to finish those off pretty quickly as well. I kind of wish I hadn't set up the second one. I wish I just set up the first one and kind of let you do the second one. But you've got it now, so go ahead and try it. See what you can do on these and email them to me. If you got any questions, shoot me an email. Grades are going in. Got a lot of people that kind of ghosted me. I don't know where you are. I'm trying to run around finding people. I don't know when this lesson should go up on Wednesday, April 29th, along with 13.1. And then on Monday the 4th will be the last of our lessons. So try to get yourself all caught up and get going. If you're watching this video much later than Wednesday, April 29th, you're falling really behind. All right, guys, good luck. Talk to you again soon. Bye.